Hi everyone. In this unit, which is one before the last unit, and it's also the last biggest unit in the course, we are going to talk about interlacing, which is the last part of the three parts that we had, the finite R transform theorem, the quadrature, and then the interlacing as part of the development of finite free probability. So the main theorem that we are going to prove is in a sense an analog to what happens in the probabilistic method, in which you know something about the expectation, and you want to understand something about a particular point in the sample space. The non-commutativity, though, it's going to be very challenging, and in particular, the expectation is going to be, as we'll see, in coefficient space, whereas the information that we want lies in the roots. So the main theorem that we're going to prove, I'm actually going to state in a second, but what I want to say is that in this video, I want to give a toy example, a simple example in which you can see this interlacing happens naturally, in a very simple example, comparably simple example, so that we can understand and appreciate how interlacing kind of comes up when you talk about the sum of two matrices and look at the characteristic polynomial of that. So this toy example is actually not going to be used in the proof. So if you want, you can skip this video, but I encourage you to look at it. I think it will give you some insights, and also there are some nice little facts that we are using from linear algebra or matrix analysis, which you may know or may not know, and it's good to just know them and see them in action. Okay, so let's start by stating the theorem that we want to prove and move to the toy example. Okay, so this is the interlacing unit, and this is the main theorem that we're going to prove. So similarly to the setup that we had in the quadrature, we are looking at two n by n real symmetric matrices A and B. So we know all eigenvalues are real. And we assume also that one, the all ones vector, is common as an eigenvector to both A and B with possibly distinct eigenvalues. Now, what I'm claiming is that there exists some permutation metric such that something happens. So what happens? So on the right-hand side, we are looking at what we looked when we talked about quadrature. It's a little bit massaged, but it's what we had there. So we are looking at the expected characteristic polynomial with respect to permutations, right? Quadrature step related that characteristic polynomial, expected characteristic polynomial with the one with respect to the Haar measure. So that's not the theme today. So we're looking at the expected characteristic polynomial with respect to polynomials, to permutations. And I'm kind of factoring out the obvious root out of all of these polynomials, the one that's common to all of them, right? Because A plus B is an eigenvalue or a root of each of these polynomials, also of their expectations, because it's the same. And what I'm looking at here then is all the factor of interest, right? All the other roots. And what I'm taking is the max root of that. So I'm looking at the maximum non-trivial root, let's call it. It's also going to happen to be smaller or equal to A plus B, but never mind that. So on the right-hand side, we have the maximum root of the expected behavior. Right? This is something that we will understand because we will understand what happens in expectation to Haar, and Haar exactly, by the quadrature result, Haar exactly kind of factors out this anyhow, right? The Haar talks about the other part, this thing. And it says that that part is the same as if you take permutations or not. And so that we will understand because quadrature will relate this with Haar, and the R transform theorem will allow us to understand what happens in the expected characteristic with respect to Haar. What this unit tells us, what interlacing will enable us to do, is to prove the following. So say we know how to bound this, then what's going to happen is that we will be able to argue about one particular point in the sample space, P0, and argue that the max root of that particular polynomial, so here there are no expectations, right? It's just the characteristic polynomial of some graph, if A and B were graphs, one corresponding to permuting B's vertices by P0 and adding to A. So the left-hand side talks about the maximum non-trivial root of that polynomial, and that theorem guarantees that a bound on the expectation, on the maximum root of the expectation, implies a bound on the maximum root of some particular instance of a permutation matrix. That's exactly what we want. Good, but as I said, before proving this theorem, just to give you a glimpse of interlacing, let's look at an example. So generally, we are interested in the spectrum of a sum of two matrices, symmetric matrices, A and B. I mean, that's what we're interested in, but usually what's happening is that we are looking at some expectation of that form. So maybe you have some distribution, how, or permutations, and you look at the expected behavior of the spectrum, where you transpose conjugate one of these matrices using your randomness. And what we are going to see in this example is what happens in a sense in the simplest case. A is any symmetric matrix, but B is a rank 1 symmetric matrix. Okay, that's an example. So you're looking at matrices of this form, A plus VV transpose, right? Because B is rank 1 and it's symmetric, so it's of the form VV transpose. And let's also assume that just normalize V so that it has a L2 norm of 1, namely V transpose V is 1. Okay? And now I'm not taking expectation over V at this point. We're actually going to be able, because it's a simple case, to understand what happens for a general V, and then we are going to also look at expectations and the expectation. So anyhow, the spectrum of this matrix is as usual. It's encoded by the characteristic polynomial, which is simply the determinant of xi minus a minus V transpose. And because this is a very simple matrix, we are going to be able to kind of quite simply relate that to the characteristic polynomial of A, and of course the information that is inside V. So let's just do that. So that's what we are looking at so far. And what I want to do is to factor things. Okay, so this determinant, I mean the thing inside the determinant I want to write as a product. So I'm going to kind of brute force factor an xi minus a out of this expression. And so the other term is going to be whatever it's required to get this expression back. So you get an I here because of the xi minus a that sits here. And then this xi minus a inverse with the minus gives you back V transpose, right? Now don't worry about like, is it invertible or not? I mean, taking the inverse of xi minus a, I mean, if I'm going to substitute for x an eigenvalue of a, it's not going to be invertible, but it doesn't matter. I'm not plugging in anything. I'm taking the inverse of this symbolic, like in terms of x is a symbolic matrix. Okay. Good. Let's clean this a little bit. Now the determinant has this well-known but kind of strong property that the determinant of AB is the determinant of A times the determinant of B. The determinant is a homomorphism, really, from the ring of matrices to the reals, complex valued or whatever. And so you can factor this determinant of products to the product of determinants, and that exactly gives you here back the characteristic polynomial of A. And not only that, it's with a product, and that's good. Because, if you have a product of two numbers and you want to understand when it's zero, then it means that one of them is zero. It's exactly when one of them is zero. We don't have like zero divisors, it's a field. So, good. So let's consider, this right expression here. You have I minus, some metrics. Let's not worry about what that matrix is precisely now, but let's focus on the fact that it's multiplied by VV transpose. And there is another little theorem about determinants, which is maybe less known. It's definitely less known than this one. It actually follows by this one, is that the determinant of I plus AB or minus AB is the same, is the determinant of I minus BA. So you can also take a cyclic shift like that also when you add to I or subtract from I. It's the same thing. And that's actually not so trivial to see, by the way, just for fun. As I said, you have some nice little theorems from linear algebra here. And the proof of that, one proof of that is you know, the hint is to look at this determinant, the determinant of the product of these two matrices, and use this, right? So compute the determinant of these two matrices once in this order and one in the other order. And when you also multiply these two matrices, you'll get I minus AB and I minus BA. So, or maybe plus AB, but it's all the same, so that you can prove that. But anyway, I'm going to take this on faith, and this means that this V transpose V, that's my B, and that's my A. A and B don't have to be of the same dimension. As long as you can multiply them, it's fine. So here it's like a row vector times a column vector. Sorry, a column vector times a row vector. And at the top and at the bottom, it's what I said before. So I can take V transpose to the left of xi minus A inverse V. And so I get this expression, right? Now, the point is that now this is a number, right? I mean, V transpose times this matrix times V is a number, and I that's written here and here always has the right size. So I here is of size n, if the matrices are n by n, and here it's of size 1, because the matrices are, the matrix here is of size 1. So it's really just a number. I1 is 1, and what you get is that the determinant of this number is exactly this number, this thing here. Just keep this one. And now let's decompose in the sense of spectral decomposition. Let's decompose A to its you know, eigenvectors and eigenvalues. So lambda I is the eigenvalues, and the UIs are the eigenvectors. When xi minus A inverse can be written like that, right? Because I commutes with A, so xi minus A has the same eigenvectors as A, and the eigenvalues are shifted according to the formula. So lambda I translates to an eigenvalue of 1 over x minus lambda I, right? So xi minus A inverse has this form, and plugging it to what we had, so this is what we had so far. So plug in this thing, this equality here instead of that, is just gives you this, just really plug and play. And now the V transpose and V, you can put them inside the sum, and you'll get V transpose UI times UI transpose V, which is nothing other than the inner product of UI and V squared. Good. So overall, what we got is this thing. Right? The expected characteristic polynomial of A plus VV transpose is related to the expected characteristic polynomial of A in terms that it's that thing times this expression, 1 minus that function that we're going to understand in a second. So the first of all to note is that if lambda I is an element in the spectrum of A has multiplicity, at least 2, then it actually also an eigenvalue of A plus VV transpose, right? Because if it appears here as x minus lambda I squared or higher, then it's also a 0 of this thing, because x minus lambda I here will, it's in the denominator, but it will become in the numerator when you multiply that out. So eigenvalue that appears more than once, it has a multiplicity in A, will appear also in A plus VV transpose. And the remaining eigenvalues, because this is a product of numbers, is okay. Eigenvalue and the remaining eigenvalues are exactly those that solve this equation. So let's look at this equation. So that's the equation that we care about, and I wrote it here. And if you draw it a little bit, it looks like that, right? So I draw the lambda i's, lambda 1 being the largest, and so forth. And then using that these are positive numbers, right? There's a square here, or none, or at least could be 0, but non-negative numbers. If you draw this, you get you get kind of this drawing that we are used to because it's related and to the Cauchy transform, and you'll see exactly in what sense. But so this is the function that's drawn here, and I also had this line, horizontal line at height 1, and the solution to this equation are exactly when the graph meets that line, namely at these purple points, mu1, mu2, mu3, and so forth. And what you can see from this is that the eigenvalues, the new eigenvalues, because the mu i's are the new eigenvalues of, namely the eigenvalues of A plus VV transpose, they interlace the eigenvalues of the lambda i's. In what sense? So, mu I is larger than lambda, mu1 is larger than lambda 1, and mu2 is smaller than lambda 1, but it's larger than lambda 2, and so forth. And that actually also applies to the case of multiplicity that we had before, because in that case, the mu I is going to be equal to the lambda I that appear twice in the same place. Okay, so there is no like splitting into two cases. There is the interlacing happening even if there is or isn't a multiplicative roots in the characteristic polynomial of A. Okay, so that's what we refer to as interlacing. You probably heard about that, but that's what I mean by that. And if you want to have some physical interpretation of that, then you can say the following. You can say, and I'm not sure how comfortable are you with that, but actually I like those things. So you can look at the trace of A plus VV transpose, which is kind of the sum of the things that you have, which you can think of as a mass or energy or what have you. Then that's a trace of A plus the trace of VV transpose, regardless of physical interpretations. And the trace of VV transpose, as before, is the trace of V transpose V, because the trace is cyclic, which is just 1 because we normalized V. So really what happens is that when moving from the A system to the A plus VV transpose system, regardless of what V is, add energy, a unit energy to the system, in a sense. And what interlacing tells you is a restriction on how this energy can affect the system. So it tells you that if you have these like billiard balls or what have you, these are the lambda i's, then when you add this energy, then every billiard ball can move to the right, but it cannot move to the right of the billiard ball that is to the right of you, right? So this could go up to here, but not here, right? The mu i's interlace each other, so lambda 3 bounds mu 3. So mu 3 can go up to lambda 3, but it can go up to lambda 2, but not to the right of lambda 2. So for example, in particular, if the lambda i's are somewhat close, then the first one, it's like a billiard. The first one doesn't have much room to move, so it moves a little bit maybe, and then the second one and so forth. And so it means that the last one has to kind of break out of the group like that, right? Because the overall movement, overall energy is 1. Okay, I don't know if it helps you or not, but I like these things. It makes me feel as I understand something that is beyond the math that I'm seeing here. And one last slide about about this two example is what happens in expectation. So in expectation, namely, I'm going to take V, which is a random restricted to it having a unit length. So in that case, if you go back to what we proved at some step of the proof, I want to visit that particular step. We had the characteristic polynomial. The new characteristic polynomial is the old one times this expression. That will be an easier step to do what I'm doing now, instead of looking at the last result that we got. So if I'm taking expectations now over V, again, V is normalized. Then, okay, this is not affected by anything. And here, the expectation kind of goes through the 1. And now, this expectation, I mean, it's not completely clear what's going on here, because the expectation of a bilinear form, but actually it's quite simple, because so you see this is, it's a number. And as a number, it's equal its trace. So this is the trace of this number, where I place this matrix that I don't want to focus on for the moment as by this rectangle. And the trace is cyclic, that's a little trick, okay? So to simplify that. So the trace is cyclic, so I can take V transpose to the other side. So that gives you that. And now, I also could have done it before, I can, the trace is linear, so I can put the expectation, switch the order of trace and expectation, really. So you have the trace of this of the expectation, but the matrix that I'm kind of ignoring does not depend on V, so I'm just writing it here. And then I'm taking the expectation of V with transpose. And if you think about it, it's just the identity. I mean, because V is, uniform over all vectors of unit length, that really means that the expectation of this thing is identity. And so what we are left with really is, okay, so we had this characteristic polynomial of A times this thing, which is 1 minus the trace of xi minus A inverse. And if you look at it for a second, this is exactly the Cauchy transform, well, unnormalized Cauchy transform that we had, right? So you can also write it as like the derivative of the characteristic polynomial divided by the characteristic polynomial. And so overall you get, so already this is a nice surprise, but at this point you get that the expected new characteristic polynomial is the old one minus its derivative. So this is something that you can actually understand, and you can actually continue a little bit more from here, but I'm just going to stop here, hoping that this two example explained or gave you some insight about how interlacing come about when you talk about sum of two matrices. And maybe I'll just remark that this difference is something we already saw. It's 1 minus U1, right? We had U alpha in previous units. It's this operator 1 minus U1 of the characteristic polynomial, and it appears here also. It's not coincidence, of course, but I'm not going to relate it much to what we did. You can, but I'm not going to do that. So again, I did all of that just in order to show you how interlacing works in its simplest form when you do a rank 1 update. And next up, we're actually going to talk about interlacing and its relation to real rootedness. So it's kind of a different facet of that thing. Okay, but I think that's enough for this video, and I'm going to continue in another video.